Okay, so we're now on the last part, mass transfer to packed beds. The first one is mass transfer to flat plate. The second one is mass transfer over or past single spheres, and this one is the last. So mass transfer to and from packed beds occurs often in processing operations, including drying operations, adsorption or desorption of gases or liquids by solid particles such as charcoal, and mass transfer of gases and liquids to catalyst particles. Now, using a packed bed, a large amount of mass transfer area can be contained in a relatively small volume. Now, the void fraction in the bed is still represented by epsilon, which is cubic meter volume void space divided by the cubic meter total volume of void space plus the solids. The values range for this void fraction from 0.3 to 0.5 in general. Because of flow channeling, non-uniform packing, accurate experimental data are difficult to obtain, and data from different investigators can deviate considerably. So for a Reynolds number range of 10 to 10,000 for gases, so take note, this is for gases, in a packed bed of spheres, the recommended correlation with an average deviation of about plus minus 20% and a maximum of about plus minus 50% is given by this, again, dimensionless factor, the J sub D and the J sub H, which is equal to 0.4548 divided by the void fraction multiplied to the Reynolds number raised to negative 0.4069. Now, it has been shown that these dimensionless factors are approximately equal, so that is why we equate them to this expression. Now, the Reynolds number is determined as based on the original formula, that's diameter times V over rho divided by mu, where d sub p is the diameter of the spheres or a particle, and V prime is the superficial mass average velocity. Now, it is in the empty tube without the packing. So, it's different than the velocity now with the packing inside the tube. So, we will have to specify really that this one is V prime, not V in the original formula, because this one was measured based on the empty tube without the presence of the packing material. Now, for mass transfer of liquids, so this one is for gases. So, for liquids in packed beds, the correlation of Wilson and Giancoupli should be used. Now, for Reynolds number on the range of 0.0016 to 55 and a Smith number range of 165 to 70,600, the equation that we should use is the one in terms of the dimensionless factor J sub D. This is equated to this expression. Now, if the Reynolds number, on the other hand, is on the range of 55 to 1,500, now this one is bigger than the first one on top, and added condition is that the Smith number range is 165 to 10,690. So if you notice, Reynolds number here is high, but in here, Smith number is only very low because it's only until 10,600. We are to use a different expression for the dimensionless factor J sub D. As an alternative for Reynolds number, now on the range of 10 to 1,500, we could also use J sub D and J sub H, which is equal to this. That is, if there's no way for us to determine as well the exact value of the Smith number. But if we do have, then we can determine both the Reynolds number and the Smith number and check which of these two equations we can use. But if there's no way of determining the Smith number, then we can have this expression as long as Reynolds number is within 10 to 1,500. Now, for fluidized beds of spheres, so our packing material is in the form of spheres in this case, which can be used for gases and liquids, and with a Reynolds number of 10,000 to 4,000, we can use the same formula that we have here on top. Okay, this one. That's equation 7.3, that's 36, this one. For liquids and fluidized beds and a Reynolds number range of 1 to 10, very small Reynolds number for liquids, this one for liquids. This is also for liquids, this one is also for liquids. We have this epsilon J sub D product, which is equated to 1.1068 times the Reynolds number raised to negative 0.72, which is actually in form comparable to the one on top, only that the void fraction was written here together with your JD factor. If packed beds of solids other than spheres are used, because this one is specific for spheres, okay, approximate correction factors has to be used for the equation above for the sphere, this one for the equation, or rather this one for the spheres, and that particular correction factor has to be stated in the problem. Now this is done, for example, for a given non-spherical particle as follow. So what we do, if the particle is non-spherical, the particle diameter to use in the equation to predict J sub D is the diameter of the sphere, with the same surface area as the given in the solid particle. The flux to these particles in the bed is then calculated using the area of the given particles. So we have to account for the actual, that is the actual surface area when the particles are not really spherical in shape. Now, what are the different calculations involved when we have packed beds or we have flow in packed beds? So to calculate the total flux in a packed bed, the J sub D is first obtained, and then the K sub C in meters per second from the J sub D. So then we can solve for K sub C if we have already determined the J sub D. Then knowing the total volume V sub B in cubic meter of the bed, void plus the solids, that is the total external area A in meters squared of the solids for mass transfer, we can calculate for the small letter A, which is the surface area per total volume of bed. Total volume of the bed, which considers already the solid spheres. So this is the formula: 6 times the quantity 1 minus epsilon over the diameter of the particle. To calculate the mass transfer rate, and that's the flux, the log mean driving force at the inlet and the outlet of the bed should be used. And the driving force, of course, we know is the difference in concentration. So the log mean of that, this expression is actually the log mean driving force at the inlet and the outlet. And we are to determine the K sub C in this case from this expression. So it's either we equate the N sub AA, the entire expression here, to this one. That way, the only thing that is, shall I say, unique in the two expression, if these two is equated, because they have the same left side, is actually the convective mass transfer coefficient. Now you have to understand that the concentration C sub I here, C sub 1 and C sub 2 has to be the following. So for C sub I, the concentration at the surface of the solid. The C sub A1 is the inlet bulk fluid concentration, inlet bulk fluid concentration, and CA2 is the outlet concentration. So the material balance equation on the bulk stream is this, which will lead us, as I've said a while ago, on the value of the K sub C if we will equate these two equations. The V that appears, where this is this one, the V that appears here is the volumetric flow rate of the fluid that enters our packed bed in cubic meter per second. So you have to take note of these different formulas for packed beds, flow in packed beds. Now we go to our sample problem, the last for this chapter, that will illustrate the use of the formulas that I have discussed. So in this particular problem, you're given pure water at 26.1 degrees Celsius that flows at a rate of 5.514 times 10 raised to negative 7 cubic meter per second through a packed bed of benzoic acid spheres having a diameter of 6.375 millimeters. The total surface area of the spheres in the bed is 0.01198 square meter and the void fraction is 0.436. The tower diameter of the packed bed is 0.0667 meters. The solubility of benzoic acid in water is given to be 2.948 times 10 raised to negative 2 kilogram mole per cubic meter. So for letter A, you are to determine or predict the mass transfer coefficient K sub C. It's K sub C because we're talking about liquids here, and you are to compare it with the experimental value that was determined by Wilson and Jean-Couplys, which is 4.665 times 10 raised to negative 6 meters per second. And then in letter B, using this experimental value, predict the outlet concentration of benzoic acid in the water. So that refers to the C sub A2. But this time, you will not use the K sub C that you have predicted or computed based on the different formulas that I have discussed, but rather you're going to base it on the experimental value that was predetermined by Jean-Couplys and Wilson. So let's go to our board to start plotting out how we're going to find our way through the maze of the unknowns in this problem. Okay, this is the third and the last on the chapter. So if we are to illustrate our problem, we have a tower consisting of benzoic acid spheres. So in these benzoic acid spheres, these are our packing materials in the shape of spheres, and their identity is given to be benzoic acid spheres. So in this column, we have water coming in. So we have pure water coming in at the condition, which is at 26.1 degrees Celsius, and with the volumetric flow rate of 5.514 times 10 raised to negative 7 cubic meter per second. This could be the volumetric flow rate. Now, that's for the water that enters our packed bed. So it leaves at the bottom. Now, in here, we have at the inlet, the bulk concentration is Ca1, and at the outlet, we have Ca2 as our concentration. Now, it is given that our benzoic acid spheres has the diameter of 6.375 mm, and the total surface area of this packing material, which are all spherical in shape, is 0.01198 square meter, and we have the void fraction, which is 0.436. Now, as to the diameter of the tower, this one, I'd like to label it as the D sub T, the diameter of the tower. That would be 0.0667 meters. And we have the concentration at the interface of benzoic acid that refers to the solubility of benzoic acid in water. That would be 2.948 times 10 raised to negative 2 kilomole per cubic meter. And so far, these are the given information in the problem. So we are required for letter A to determine the K sub C, and it's to be compared to the experimental value that was stated. And letter B, we are to determine the outlet concentration using the experimental value that was given, not the calculated value that we will be determining based on the required information. Now, just like any problem that we have started in here in terms of mass transfer coefficient in various geometries, we always start with establishing the velocity profile. We can start with the formula, but it helps that we will establish the velocity profile. So we will know what formula we are to use because we have different formulas based on the value of these dimensionless numbers. That will give us the identity, or that will establish the velocity profile. So for our Smith number, and this is 26.1 degrees Celsius, we'll be using the property of water still because we have a dilute solution, mu rho, then the molar diffusivity. And if it's water, so for water, for H2O at 26.1 degrees Celsius, our mu is 0.8718 times 10 raised to negative 3 Pascal seconds. The density is 996.7 kilogram per cubic meter. And we are to determine as well its viscosity at 25 degrees Celsius, which I will point out to you later why. So which is 0.8940 times 10 raised to negative 3 Pascal seconds. Now, knowing this, we can go back to our Smith formula and substitute. So 0.8718 times 10 raised to negative 3, we have to divide it by 996.7 multiplied to our molar diffusivity. So take note, this is our Smith number at 26.1 degrees Celsius. So take note, I did not place any value for the molar diffusivity because the problem that does not give us this one. So I'd like to have this as equation 1. So we will use the molar diffusivity that is provided from a table, a property table giving us the molar diffusivity of the system, benzoic acid, and pure water. Now, if you recall, we have this particular table in the chapter on diffusion, and that table is table 6.3-1. It gives us the molar diffusivity of benzoic acid in water, and that's equal to 1.21 times 10 raised to negative 1 meters squared per second. However, this table gives us the molar diffusivity at standard condition of 25 degrees Celsius. Our problem has the temperature at 26.1 degrees Celsius. So there's a need for us to correct this value that we have taken from table 6.1 to the temperature in which our system is, or the condition in which our system is. So it's 26.1 degrees Celsius. So how do we correct this particular DAB to the temperature which is 26.1 degrees Celsius? Now, DAB is actually directly proportional to the absolute temperature and the viscosity. And you have learned that whenever we replace a proportionality symbol by an equal sign, we introduce a certain constant. Since we're using K here, I'd like to change this constant to K prime. That way you will not, or K double prime, that way you will not get confused. It's the constant after we have changed the proportionality symbol to an equal sign. And this will be multiplied to T over mu. So I'd like to determine this constant, because this one, since it's a constant, it doesn't matter what temperature are we determining the molar diffusivity. So for example, since I know already the molar diffusivity at 25, so I will have 1.21 times 10 raised to negative 9, and I will have the constant K double prime here, and I will multiply it to the temperature at 25 which is 298, and our mu at 25, which we determined here, so 0.8940. So 0.8940 times 10 raised to negative 3. In this process, we get to know the K double prime, which we will use for a different temperature of for the different temperature in which we are to determine the molar diffusivity. So in this case, your K double prime is 3.63 times 10 raised to negative 15. Now I will use this same constant when I determine now DAB at 26.1 degrees C. So that constant, which is 3.63 times 10 raised to negative 15, will now be multiplied to the new temperature, which is 299.1. This is for the 26.1 degrees Celsius, divided by the mu at this particular temperature, which is 0.8718 times 10 raised to negative 3. So now I have a corrected molar diffusivity at the indicated temperature, which is 1.246 times 10 raised to negative 9 meters squared per second. Now, having the molar diffusivity already, I can go back to my Smith number here from equation 1 and determine its value. So we'll go straight to the value of the Smith number. So from 1, you'll get the dimensionless number Smith number equal to 702.34. Now you have determined it. We can go now to the Reynolds number. Our Reynolds number is dV prime density over mu. Now our diameter is the diameter of the sphere, not the diameter of our column. So in this case, the diameter of the sphere in meters will be 0.006375. And this velocity here, class, is the velocity of the fluid that is passing through, and that in case it's water that is passing through our packed bed. So this velocity will be computed now. Our velocity will be based on the volumetric flow rate of water to our packed bed, which is 5.514 times 10 raised to negative 7. If this volumetric flow rate is divided by the cross-sectional area of the tower, that will give us the velocity, or the superficial velocity. So we will divide this by the area of the tower, which is pi d squared. The diameter of the tower is 0.0667 meters. So we will square this, pi d squared over 4. So your division by 4 here will now give us the area. If we divide this volumetric flow rate by the area, that gives us the velocity. Now the density is the density that we got initially for water. So this is 996.7. Our mu is 0.8718. That's for our Reynolds number. So by the way, this is times 10 raised to negative 3. This will give us a Reynolds number equal to 1.15. Now, for dilute solutions, we have K sub C prime being equal to K sub C, and we have this appropriate JD from what we have discussed based on the Reynolds number value and the Smith number value that we got. So it's 1.09 over the void fraction times the Reynolds number raised to negative 0.67. This should be equated to the original dimensionless factor J sub D that we've discussed, that would lead us to the convective mass transfer coefficient K sub C, and it's under the topic of dimensionless numbers used in correlating data. So this will be K sub C prime over V prime multiplied to the Smith number raised to 0.67. So this one, it came from that correlation of the dimensionless numbers. This one came from the series of formulas that we are to choose from, and we choose the formula that is appropriate for the value of the Smith number and the Reynolds number that we got in this problem, and that particular formula is this one. So if we will determine the K sub C prime based on these two, if we will equate the two, that would be 1.09 times the Reynolds number raised to negative 0.67. If this V prime is the divisor here, so that we keep the K sub C prime in here, then it will appear in the numerator. Then we have in the denominator N sub C raised to 0.67, representing our Smith number. So now we can do substitution. Our Reynolds number is 1.15. We raise it to negative 0.67. Our V prime is determined based on what we have in here. This entire expression. That's our V prime. So that's the same V prime that we will have in here. I will just transfer the 4 in here. So we'll have the pi 0.0667 here, which is squared. So this is our Reynolds number, this is our velocity, and we have the Smith number, which is our Smith number in this case is 702. .34, and this should be raised to 0.67. So let me check. And we have in this case also weight, so 1.09. So we miss the void fraction here. 1.09 Reynolds number over this. If this is the divisor, this one goes up, and that's it. So we need to multiply our 702 by 0.436. 702 Okay, so our K sub C in this case now is 4.448 times 10 raised to negative 6 meters per second. The experimental value that is stated in the problem, where we need to compare this one, is 4.665 times 10 raised to negative 6 meters per second. So the value does not really change that much. So it's still pretty much the same. Okay, so we have this already. Okay, this is our answer for the K sub C. So our first requirement is we determine the K sub C. This is actually K sub C prime, but K sub C is just equal to K sub C prime because we have a dilute solution. So for the last part, we are to use the experimental value that was given in the problem in determining the shall I say, the concentration at the exit of the tower. So we'll have the formula for this in this case will be the same formula that we have used here, but I will change this one to this one, the 4.665 times 10 raised to negative 6, and we will use the formula that is given in here, a formula that equates these two. So we have this expression, this and this. So if we will equate these two, you will have a Kc value. So it's just like Kc is equal to V over A. If I will transfer, if this entire expression is equated to this, we want to isolate the K sub C here. So this A times this log mean driving force will be the divisor of this entire expression, right? So I will equate the experimental value by V over A times CA2 minus CA1 over this log mean driving force. I think you know how to follow through the math. So if you do that, this will be the resulting expression that you will be getting. Have a new sheet for this. You will have a K sub C, the experimental K sub C, you have K sub C being equal to, so that would be the V over A times CA2 minus CA1. Then this one will be the log mean driving force multiplied to the log mean driving force. The log mean driving force is CAI minus CA1 minus CAI minus CA2 all over the ln of the two expressions here. CAI minus CA1, CAI minus CA2. So we just copied. I got this from equating this K sub CA, this one, to V and this one, because both, as shown to you, is equal to NAA. So we have already this. So we have here the experimental value and the volumetric flow rate. I'll place here 5.514 times 10 raised to negative 7, and we are to multiply it with the CA2, which we are looking for. We subtract CA1, which is 0. That is the concentration of, in this case, our sphere is benzoic acid at the inlets. We don't have it because it's all water, pure water. Then our area, I predetermined that to be 0.01198 using this area, by the way, is the total surface area of all the spheres which were used as packing material. So 0.01198, and we multiply it with this log mean concentration difference. So our concentration at the interface is 2.948 times 10 raised to negative 2. We have a 0 for CA1. We have another 2.948 times 10 raised to negative 2 here, minus CA2. And then we have the ln of 2.948 times 10 raised to negative 2 over 2.948 times 10 raised to negative 2 minus CA2. Okay, this is our entire denominator. If you do the maths, your CA2 value, that is the concentration of benzoic acid at the exit of your tower, is 2.842 kilomole per cubic meter. So this is the second requirement. The first requirement is we determine the mass transfer coefficient, And that's the first requirement, the mass transfer coefficient. And the second requirement is we determine the concentration of benzoic acid at the exit of the tower. So this already concludes the chapter on unsteady state mass transfer, including convective mass transfer, considering all geometry. So the only thing that was not included in the chapter are those methods which already considers chemical reactions and uses already numerical methods in the processing of the data that is provided in the problem.